So,
All right, so hi everybody. Oh, come on, guys. Let us try again, please. Let's try again. I'm Nigerian. We love energy.
and
Hi,
I'm Brazilian.
everybody.
Yeah, we love energy
Yes,
too.
much better. Glad to be here. I'm here with my colleague Rafa, and we've got 50 minutes to take you through this really interesting topic. We presented this at DevOps France 2 weeks ago, or 3 weeks ago, and we
Yes.
got lots of positive feedback, and we can't wait to share all of that with you. So this is like an improved version over that in the first place.
Yeah, let's just ask them. Who is already building agentic applications? Anybody? All right. What about RAG pipelines? Has anybody built RAG pipelines? All right. Is anybody using Spring AI already? Just one hand. Okay. And who came for the human part of the talk? Just a few hands. And who came for the agentic part? Probably the rest. Okay, just a few hands. Who came for nothing? Because what's going on? All right. Okay, that's all right. Let's.
This
let's
is
keep
interesting
going.
because in France
Yeah.
we had more people come for the human part than the
Yeah,
agentic
like
part.
90%
So
of
this
the
was
crowd.
really good.
Yeah.
But anyways, we'll be talking about agent memory, but memory from the perspective of both humans and AI agents. I will tell you lessons that you can learn from both. But very quickly, who are we and why should you listen to us? I'm Samuel. I'm a developer advocate at Redis. This is my third month with Redis. But prior to that, I was at JP Morgan, where I worked for 6 years on the applied AI team. And I've got Rafa.
Yeah, my name is Raphael De Lio. I also work as a developer advocate at Redis. I've been there for like 2 years. Before that, I was working mostly with distributed systems, basically Java and Kotlin most of the time. I've also been working as an AI engineer at Redis for 1.5 years, more or less. And I'm also leading the Dutch Kotlin user group in the Netherlands. So is anybody from the Netherlands here or based in the Netherlands? Okay, a few hands. Next week, we're going to be having a new edition in Amsterdam. So if you're close, come by. It will be super fun.
Yeah, awesome. Now, something that is not on this that I think is worth paying attention to is, guys, we are not cognitive scientists, right? We're just software engineers that have this deep interest in cognitive science. And this is based out of like our research and our learning. So please, as much as possible, even though we try to be very accurate, take what we say with a pinch of salt, but still believe us as well. So why do we care about this topic? It is really important because like AI agents now, the memory space is exploding. And I will show you about this shortly. And they've got a huge challenge which we will try to like address. But first of all, let me run you through the agenda for this talk. We'll start by understanding what memory looks like in large language models. Large language models are stateless, but they actually have a form of latent memory, which we'll talk about. We'll talk about the anatomy of human memory. This is the most biological cognitive science aspect of this talk, and Rafa will be handling that. But it's going to be interesting as we've got lots of personal examples. And then we'll be talking about lessons that we've learned from the human memory, and also based on the challenges of several clients that we've worked with in Redis, that we can apply these lessons to in agentic AI memory. And I'll be giving you an actual live demo, one that actually hopefully works this time, right? So let's get into the challenge pretty quickly. LLMs out of the box don't remember you across interactions. And I put out of the box intentionally. This is because LLMs are built on a very popular deep learning transformer architecture, which actually aims for them to be stateless. So they actually don't carry the information you say across board. Right? So, but this sounds like a simple thing to gloss over, but think about the implications of this. Imagine having a coding agent that doesn't remember that you prefer Python over Java, if you do, and every time writes in Python. That can be troubling. Or you have to keep telling it your preferences every single time, because memory is huge. So as humans, we realized how important this was over the last couple of years, and every player started getting involved in this space. Every major AI assistant now supports cross-session memory. From Claude to Gemini to ChatGPT, this happened over the course of 12 to 18 months, and we just see this traction growing more and more. AWS, Azure, Google, all hyperscalers now have their own managed memory services, which was something that we didn't have in the last couple of years. And the number of open source memory frameworks is growing really rapidly. Part hype, part true, but it just shows you that there's lots of movement here, right? So this is fine and this is good, but what is memory really? Like as software engineers, we've constructed models for many other things in life, right? So for example, for things in computing, we have the networking OSI model, which is a good abstraction. Even for data, we have the relational data model for databases. But for memory, do we have any model for this? And how can we actually apply this into your applications? To solve this, there's a quote by Albert Einstein. He has so many quotes attributed to him, so I don't know if this is true or not. But he says, look deep into nature, and then you will understand everything better. We see this pattern already. In fact, there's a field called biomimicry, where we try to copy nature to influence our technology. Airplanes, even though they don't flap their wings, inherit some of the thinking of how birds fly, right? So what can we learn from humans that can apply to AI agents? But first of all, let's start with LLMs first of all. Let's look at what memory looks like in them. Now, I mentioned that LLM models are stateless, but they have two forms of memory. Now, I'll explain that shortly. They've got the parameter space, and they've got the activation space. So the parameter space is about the memory that was baked into the model itself based on training. I'll talk about the training data very, very shortly. But the way LLMs were trained was actually they were run over like millions of texts and corpuses. And then these texts actually have their value encoded in the weights of your LLM memory. Which is why if you ask an LLM about what's the capital of Paris, it will tell you the answer because it's had that information in its training set, right? The activation space, however, is slightly different. This is the space where your contexts live. Anytime you ask a question, those questions actually form activations across the weights and create this latent memory, which most people call the context window, right? This is finite in a sense, but also does not carry on across sessions. So let's look at the training process for LLMs, as I said earlier. The earliest sets of like ChatGPT 3.0 and 3.5 were trained on a text corpus called the C4. And data from your Wikipedia, your Reddit, the internet essentially was scraped. The last I checked, this text was about 750 gigabytes of data. Like really, really huge, right? And this is what it looks like. Essentially, what you're doing with LLMs in your training is that they're auto-regressive. So they're trained to predict the next word given a particular series of text. So if I say, for example, that's one small step for man, what should follow? A giant step for humanity, right? So what we then do is in this parameter space in the training, when the LM predicts one, we give it like a reward to say, hey, you're on the right track. And if it predicts one that is not correct, you can then rewire the weights so it predicts the next likely one. LLMs are auto-regressive, but again, their parameter space has this feature where you have to have these huge loads of text, right? If I give the example I gave here about this boy made a mistake, if he were a man, it's predicting one here, whereas we want to predict he. So what we do here in the training data set actually is we like back propagate the error back to the weights so that the weights are reflected of what it should be. Now, let's look at this now. You can see the like activations. This boy made a mistake if he were a man, and now we have like the right one. It is he that is being produced, right? And that's the like general like idea behind the parameter space. But we saw this video that shows you just the scale, because someone might think, well, if LLMs can perform this training across multiple texts of data, why can't we just create different models? So this video shows you something interesting, that if you were to like have a billion computations per second, I think, would the LLM training take a second? Will it take, for most modern use cases, would it take a minute? Would it take an hour? Would it take a day? Would it take months or even a year? Turns out that the scale of building LLMs is actually so complex that it could take up to 1 million years, actually. This is not something anybody can just delve into. So there's already some limitations from the idea of training, where you cannot just randomly train your LLM text on new data, right? So just to give a quick recap, your parameters, they do not store your exact documents or explicit memories. There's no place you would go to in a model that you would see the text, the capital of France is Paris. Right? What it does actually is that it encodes that meaning across the weights. And this is really, really important because this statistical pattern is what makes the LLM able to generalize across text. Now, the parameters are fixed once they have been tuned. There are some ways that you can, fine-tune, for example, your training sets, and you can like retrain on new sets of data. But as I mentioned earlier, in the case of retraining, this is not trivial. And in fine-tuning, there's this result called catastrophic forgetting that says when you have an LLM who is fine-tuned on new data, it performs poorly on the previous data. So how can we extend memory beyond what has been trained? Well, let's look at someone who almost mimics LLM. This is Nigel Richards, and he won multiple world championships in English Scrabble. He's like a genius at Scrabble, right? And then he then thought, this is not challenging enough. I need to go to France and try to win the French Scrabbling competition. And he won the French Scrabble competition without learning French. What he did essentially was going through all the Scrabble dictionary of words and like memorizing that. And then based on that, he was able to, given the tiles of the Scrabble tiles, predict what words can be formed out of that given what he has learned. So in a sense, he was like an LLM, in a sense, right? Because he encodes information he has learned and uses that to like predict new things. Let's talk about the activation space. This is what we mean by your context window. So after training, your model weights are fixed, correct? But then the next time you interact with the LLM and you want to like perform inference, because remember I said this earlier, LLMs can be auto-regressive. That is, they generate words after the other. The next time you say that's one small step for man, that text in itself is encoded in the activation space. It then tries to predict the next word based on that. So it already has this that's one small step for man. And this is how it works. You've got this input, that's one small step. The step gets added back to the activation space, and then you have for gets added, and then you say, okay, well, if we can have context windows that are large and you can have this memory in form of context windows, why can't we just have huge context window sizes? I mean, I gave this example in the talk earlier this morning, that it's not uncommon now to see models that have 1 million tokens as context sizes, right? Well, there are two problems there. One is the transformer architecture, which is the way these LLMs were trained on, uses the attention mechanism. And what happens behind the scene is that every token in your words actually attends to every other token. So if you've got a double increase in your token count, you actually have a quadratic increase in the computation across that. So again, it is not cheap. And then there's also a research that was done that says if you have huge context windows and you try to put relevant information in the middle, your LLMs have more difficulty retrieving information from the middle as opposed to information from the beginning or the end. So there's a lossy form of memory, right? So let's do a very quick recap. For the activation space, every information needs to be present in the context window. If you have new information that you want to add, and the context window doesn't support that, that's on you. It's limited in length. And then scaling that length of the context window is very, very challenging. There are some workarounds which exist in the research community, but this leads to imprecise responses. Now, we say this both to say, even though you have memory, in a sense, in large language models in the form of the parameter space and the activation space, they are quite limited, which begs the question, what are the new techniques that we can learn from here? And from here, I'll hand over to Rafa, who will take you through the journey of the human memory and how lessons that we can learn from here. Thank you.
Thank you, man. Yeah, so guys, this part of the talk is actually based on my research that I did last year. When all of these agents started getting to agentic memory, I started trying to understand where this inspiration came from, and that's when I started diving into cognitive science a little bit, reading books and also watching some videos and understanding the models and so on. And that's why we decided to actually make this talk, to share a little bit of this knowledge with you all as well. And when you start learning about cognitive science and human memory, one of the first cases you come across is this one that was basically, so let me just take a step back because my memory is not actually working really well right now. But actually, Nigel Richards is not the only human to have ever kind of operated a little bit like an LLM or an agent. We had this other use case as well, this other case that is HM. He was an American guy back in the 50s, and he suffered a lot from seizures and epileptic attacks. And he went through an experimental surgery at the time to see if he could minimize those seizures that he had. And the doctor at the time decided to remove part of his hippocampus, trying to minimize the effects that he had. And it kind of worked, but there was a side effect that came from that, where he basically could not encode new long-term memory anymore. So everything that he had learned until that point, he could still recall. So his name, he could still remember the Second World War, he could still remember the Great Depression in the United States, but everything that he'd learned after that, he could not retain. He would forget everything in like 15 minutes. And it was a very important case in cognitive science because until that time, doctors and researchers, they understood, where is it? That memories were scattered all over the surface of the brain. But because of his surgery, they started understanding that different parts of the brain were actually responsible for different types of memory as well. And along the rest of his life, he lived until 2008. He was used for research, very happily. He didn't live badly or anything like that, to understand how human memory works. He's not the only person you come across when you start learning about cognitive science. Another person you easily or quickly come across is Richard Atkinson. And Richard Atkinson is one of the founders of cognitive science. When I was watching one of the videos where he's talking about his research and his biography, mostly, he mentioned something that I wanted to share with you all as well, which is this quote where he says that he and Joe McCarthy, the founder of AI, was a close colleague at Stanford, and that their research groups shared the PDP-1, which was the first transistorized computer on the west coast of the US. And that's to say that cognitive science and artificial intelligence are two subjects that kind of emerged together and evolved together for a long time until they separated and each one moved their own way, as you're going to understand why later on. All right, but that's not the reason why Richard Atkinson is so important to cognitive science. Actually, he was the first person, together with his colleague Schifrin, back in 1968, to present a unified memory model for humans. And it was revolutionary for two reasons. The first one is that he was the first one to explicitly state that we have different types of storages in our brain. So a sensory storage, a short-term storage, and then long-term storage. So basically, your sensory store is based on your senses, right? Your vision, your hearing, your touch, and so on. So if you're paying attention to me right now, and you close your eyes, and I ask you, what's the color of my pants? If you hadn't paid attention to that, to the color of my pants until that moment, when you close your eyes, that information will be gone, right? Unless you had paid attention to that. Now, if you open your eyes again and look at my pants, you're going to remember the color. And if I ask you to close your eyes and repeat the question, you're going to remember what color my pants are, because that information have been transferred to your short-term store because you paid attention to that information. So even though it was on your site, if you don't pay attention to that, this memory is going to be gone really quickly in a few milliseconds if it's stored in your sensory store. However, now that you paid attention to this and you remember the color of my pants, if I ask you again, you're going to remember. But if I ask you tomorrow, chances are high that you may have forgotten, right? That information. Maybe not, because I made you pay a lot of attention to that, and now you may want to remember that. But there's a lot of things that you may forget if you don't transfer that to your long-term memory. And that's where this model was also revolutionary, because we knew that there are long-term memories. We knew that they came from short-term storage, but we didn't know that we could deliberately transfer that memory from short-term storage to long-term storage as well. And you can do that through repetition, for example. So if you keep repeating a number, you're going to remember that number later on, and maybe for the rest of your life. Like, I still remember my phone number from when I was a kid, even though I don't have this phone number for like 20 years now, right? And pretty sure that you have a lot of information like that is still retained. And that's to say that at any moment, you can also lose information from these stores. So as I mentioned, the sensory store, the information that is stored in there is retained for like a couple milliseconds. The short-term store, the consensus is that it's about 15 minutes. And the long-term store, there is research that says that we actually don't forget, but the recalling of memory decays within time, especially if you don't recall that memory very frequently, or if you don't have a strong emotion attached to it as well. So this is the first memory model to be introduced. And now what you're going to do is you're going to zoom in each of these types of storage and look at how they were evolved or how they were researched a long time as well. So the first one you're going to look at is the long-term memory. And you're going to look at another unified model that was presented back in 1992 by Larry Squire. So the type of long-term memories that are presented here were not discovered by Larry, but he was the first one to unify all of them in a single memory model. And the way he did it was by actually separating them into two different categories. So you have the declarative type of memory and the non-declarative type of memory. The declarative one is the one that you can easily declare. You're not only aware that you have this memory, but you know exactly what this memory is composed of. While the non-declarative one is the one that you cannot really tell, but even though you may be aware of that, like you know that you have the memory to ride a bike, for example, but you cannot really tell how you ride a bike, right? You have an idea, but you don't know exactly which muscle you gotta move in which moment and so on. So this is non-declarative types of memory, right? You're gonna take a closer look to all of them, but you're gonna get started with the declarative type of memory. The declarative type of memory is the type of memory that when you're building agentic applications, you usually integrate into your systems. And this comes from an inspiration from the human memory. So we have two types, the semantic memory and the episodic memory. The semantic memory are those memories related to facts and general knowledge that you retain. So for example, you know what the capital of the UK is. You know what the capital of France is. Those are all semantic knowledge and semantic memory. Because you don't exactly remember what was the episode in your life when you acquired those memories. Potentially for the two ones that I mentioned, right? Unless you remember exactly when it happened, how you felt, who you were with. If you have all of this information, then it becomes episodic memory. And I have a great example because I got a dog, his name is Pongo, and he's obsessed with the ball, right? I know that he's obsessed with the ball as a fact. This is a semantic memory that I have. But I don't know exactly when he became obsessed. I know that when he was a puppy, he didn't care about the ball at all, but at some point he started caring about it. But I don't remember when it happened in his life, neither in my life. However, I have a lot of episodic memories associated to Pongo. For example, the day that we got him. And it was back in Portugal when I lived before, in a very sketchy place, with a very sketchy guy. He parked a small truck. He opened the back doors. There were like 3 dogs in there, a beagle, and 2 dogs of the breed of my dog. Another family came, took the beagle. My wife and I came, and we looked at Pongo, and we loved him at the time. We got him, we put him in our car, and you can see that his body is white, and then a lot of black dots started surfacing from his fur. And you're like, okay, he's got fleas. We got to take him to the vet. I told my wife we're not taking him home. We're going to take him directly to the vet. So I have a lot of information related to this memory, and that's why it's an episodic memory, right? Including emotion, time, and so on. So those are the declarative types of memory. We also have the non-declarative types. And here we're going to talk about 4 of them: the procedural, the priming, the classical conditioning, also known as Pavlovian, and the non-associative learning type of memory. So the first one is the procedural one. We all kind of have an idea that we have this memory. It's usually known as muscle memory, even though we know that it's not stored in your muscle, it's stored in your brain, right? And it's related to cognitive and motor skills. As I mentioned before, like riding a bike, typing on a keyboard, playing a musical instrument, or even like reading or language patterns as well. If you have learned a second language, or if you have taught a second language as well, you know that you cannot teach a language. You can only acquire a language, right? So even for kids, they need to learn by themselves. You cannot tell them exactly what they need to know for them to learn a language, even though there are parts of the language that are associated with semantic memory as well, like the meaning of words, for example, the pronunciation. But the actual fluency comes from procedural memory. Then we have the priming type of memory, and this type of memory is strongly taken, marketeers take a strong advantage of this type of memory. And this is the one that you get one thing and you associate that to another thing, even though you don't remember exactly why you associate these two things one to the other. We just had Mother's Day, I think this Sunday, right? In Brazil, it's like in the second Sunday. I think in Europe, it's on the first Sunday. And if you go to supermarkets on that period, you're going to see like a sign saying Mother's Day, and next to it, in the same corridor, for example, you're going to see flowers being sold or chocolates or things like that. Because you're going to pass by, you're going to look at the sign, you're going to associate that you need a gift, right? So this is priming memory. And if I show you this image, for example, and I ask you about a beverage or a drink, what's the first drink that comes to your mind? What? Red Bull, right? So most people are going to associate radical sports with Red Bull. And somehow they were able to do that by taking advantage of our priming memory. But not only that, if you think about Coca-Cola, for example, what comes to your mind? Christmas, polar bears, happiness, sometimes even sports, right? They try to associate them with sports. But then if you remember, Cristiano Ronaldo kind of broke it by pushing away the bottle of Coke. But that's how the primary memory kind of works. Then you have the classical Pavlovian conditioning, right? And this one is separated into two different types of them. You have the emotional and the skeletal. The emotional one is the one associated with emotions, basically. So, for example, if a person hears a dog bark and then gets bitten, later any dog bark produces a fear reaction, even though they don't pose a threat, right? So you can get a small poodle if somebody listens to them barking, somebody that went through this thing. After that, they're also going to be afraid of the poodle somehow, right? And then you have the skeletal one that is similar, but it's not really associated with emotions. It's more associated with actions. So, for example, whenever I'm driving my car and my wife is in the passenger seat, let me just tell you this, because I'm a terrible driver, right? So she always tries to press the brakes that don't exist on her side of the car, because I'm getting too close to the car in front of me, or I'm doing something that's not very... That is very dangerous, right? So this is a skeletal type of classical conditioning memory that she has. She knows, first of all, that when I'm driving, it's dangerous, and she knows that she has to press the brakes when we get too close to the car ahead of her. And then you have the non-associative learning type of memory, and you have two types, the habituation and the sensitization. And if I stop talking, you can listen to this humming sound, right? To this white noise. Had you realized that this noise was here before? Probably not, because your brain had habituated to that sound automatically for you. You don't even know that you have this memory, right? But now that you paid attention to it, you probably won't forget until the end of the talk. And then you have sensitization, which is the opposite, where basically when I'm watching a horror movie at home, after that movie, I start paying attention to all the noises that my house makes, even though I never realized that it makes all these sounds. So I become much more sensitive to them. And those are all the types of long-term memory that Larry Squire unified in his model back in 1992. We also have working memory, which, as I said before, is our consciousness, right? And there's another model that I want to present to you, which is the one that was presented back in 1974 by Baddeley and Hitch. And back in the time, this model was composed of three different structures. So the central executive, the phonological loop, and the visual spatial sketchpad. And I said structures because the central executive is not a storage. It's just an orchestrator, basically. But the phonological loop and the visual spatial sketchpad are actually storages. And then back in 2001, they revised their paper and they also added the episodic buffer storage as well. So let's take a quick look at each one of them very briefly now. So the central executive, as I said, it's kind of our orchestrator in our brain. It kind of controls what we're paying attention to, what kind of memories must be retrieved from our long-term storage, and so on, right? So right now, we're all here, for example, or let me give you another example. When I'm at home, for example, I like to work from my office, but sometimes I like to work from the kitchen. And then I get my computer and I go to the kitchen. And somehow my brain knows that even though I'm in the kitchen, if I'm with my computer and I have a task in hand, it knows exactly what to pay attention to. It's not going to pay attention to the oven, it's not going to pay attention to the fridge or other things. However, if I start cooking, for example, then my brain is going to know that, okay, I need to pay attention to these other things now. I have something on the oven, I have something on the stove, and so on. And this is the part of your brain that orchestrates your attention. And then you have two other storages, the phonological loop. So the phonological loop is basically our inner voice, and it's composed of two different structures as well. So you have the acoustic store and the articulatory loop. So the acoustic store is that sensory store that we talked in the beginning, and information is retained there for only a couple milliseconds. And that's why you also have this articulatory loop, where you basically keep repeating the information in your head, or at least part of that. You cannot remember exactly the words that I mentioned, that I just said like a couple seconds ago, but you can remember the general idea, because you keep looping that general idea in your brain, trying to follow up follow along the talk that we're delivering right now. But the information that is in your articulatory loop doesn't come only from the outside world, it also comes from your brain itself, so your long-term memory or your working memory and the information that you're working with at the time. So this is the phonological loop. We have a similar structure that is the visual spatial sketchpad. So it's also composed of two components, so the visual cache and the inner scribe. And the visual cache is the sensor store, and the inner scribe is this sketchpad that you have in your mind that allows you to deal with reality, to walk around, to balance yourself, to know where things are, to navigate, and also to imagine things in your brain, or think about, like if I show you this pointer, you can look at it and try to rotate that in your brain, and this is because you have the visual spatial sketchpad structure in a type of memory. And then you have the episodic buffer, which is basically where the long-term memories that are currently needed are stored in your working memory so that your brain can work with that later on or during the current task that you're dealing with at the time. Now, there are some similarities and differences between human memory and, let's say, machine learning memory, right? There are a few similarities. So, for example, both depend on pattern recognition to process information, even though the way it works is a little bit different, as you're going to see. Both use context to guide interpretation and recall. As I was telling you, if I'm in the kitchen, but I'm with my computer, my brain knows which kind of information it needs to recall from my long-term memory. And so does agentic memory, as you're going to see, but in a different way. Yeah. And both show position-based effects similar to primacy and recency. So this is exactly what Samuel was talking about in the beginning of the talk, where he presented the concept of lost in the middle. We know that humans, based on research, usually can remember what has been presented to them in the beginning and in the end, but what's in the middle, it's more difficult to recall. For example, if I present you a list of 10 numbers, you're going to remember the first numbers, you're going to remember the last numbers, but the ones in the middle is more difficult to recall. And somehow, LLMs, they work similarly. So if you present them a context with a lot of tokens, they can pay attention to the ones that are in the beginning and in the end more precisely than they do to the ones that are presented in the middle. So those are a few similarities, but there's a lot of differences, as you may have imagined. For example, if you think about long-term update, in humans we have this continuous biological learning, but in LLMs, they're only updated via training or fine-tuning. So they're fixed, as Samuel talked in the beginning, right? They cannot really learn anything new because they're stateless. And then you have the recall mechanism. So for humans, have cue, context, emotion dependent, as I was talking about the kitchen, for example. But for LLMs, it's only probability, right? There's a statistical completion that it does. If you think about forgetting, in the long term, in humans, as we mentioned, have this adaptive decay and interference. In LLMs, they don't forget. So if they were trained in a data set that said that, let's say, that the queen was alive, and nobody, and people keep using the same data set after that, it's not going to know that the queen has died, even though you may present this information to it later on. So you need other strategies, as you're going to see, for it to remember and forget as well, right? And then you have intentional retrieval. So humans can deliberately search memory. We have intention on our tasks most of the time. But LLMs, they don't have any internal goals or search processes. They just follow these statistical completions, right? And now, before I pass back to Samuel, I just wanted to talk about this quote as well, which is, it's not because an airplane doesn't fly like a bird that it means it doesn't fly. So as I said in the beginning, cognitive science and artificial intelligence, they emerged and evolved together, but at some point they had to split and each one followed their own path. And if you think about airplanes, for example, for millennia, humans have tried to fly by mimicking birds, and they failed every time. And only when they stopped really trying to mimic birds precisely, that's when we started flying with airplanes the way we know today. But it doesn't mean that we still cannot get inspiration from nature and try to make our airplanes more efficient and fly better, consuming less fuel, and so on. In fact, now they're researching a new type of airplane that mimics dragonflies, and it's kind of working, apparently, right? But that's to say that it's not because an airplane doesn't fly like a bird that it means it doesn't fly, the same way that it's not because a computer doesn't think like a human that it means it doesn't think, even though I'm not stating that. I'm not saying that computers think. That's not what I'm saying. All right, so back to you, Samuel.
Thanks. Oops. Now that we've understood like the basics of cognitive science and how human memory works, it's time to then come back to AI agents. Now, at Redis, we've worked with several clients across various domains over the last couple of years, right? And we've seen a couple of patterns, particularly challenges in the agent memory domain. And there are three of them that keep coming up over and over again. And so we'll see what these patterns are and then how we can apply learnings from the human aspect to solve these patterns. And we've got a demo for you at the end that actually implements this. It's stock chat application that you can ask questions around your stocks. So let's see the patterns. The first pattern is how to acquire memory, the problem of acquisition. Because here's the thing, as users interact with your AI agents, remember that you've got finite storage and you can't just simply dump every single thing you have into your context. A good question to ask is, what determines what part of this user's interactions that I store? I can't just store everything, even though we see patterns now with people trying to like just dump everything you have into a database and retrieve that. That hasn't worked too well. So that's the first challenge. The second one is how do we manage memory? Because memory has a life cycle. Not all memory is created equally. Some memory should be forgotten after a day. Someone should have a more persistent lifetime. If I ask, for example, a shopping agent, for example, how many, is this item still available, right? By tomorrow, it's possible that that item is actually off the shelf and there's no more item in the inventory. So we need to figure out how do we manage these differences between memory that changes over time. And then very, very importantly, all your memory is useless if it can't be retrieved. You might have the best memory in your database, but if you don't get to that when the user actually needs it, it's a challenge, right? So how can we do that?
In the right context as well.
Yeah, in the right context as well. So with that, we have the Redis agent memory server, which we spoke about very briefly in the earlier session, but I'll go over this quickly so that we can go into our demo. But we take the concept of the long-term memory and the short-term memory from humans and use that to actually encapsulate a system called the agent memory server. And what it does is that the agent memory server using Redis as your data store actually allows you to like store things in your working memory that are the conversations you're having with your users currently. Like for example, I can store the last 10 or 20 conversations I have with a user just so that I can keep on referencing that. But there are some things that should persist beyond a session, right? Like persistent facts or information about something I want to use later on. So we support the idea of having like topics, vectors as well, can be stored. But very, very importantly, the agent's memory server allows you to automatically extract long-term memory from your working memory. So if a user says something really interesting, the responsibility is not on you as a software engineer to figure out how do I store this in the long-term store. The agent memory server does that for you behind the scenes, and I'll show you how. Let's look at each of them quickly. How do you decide what to extract, right? So I mentioned earlier that we need strategies to solve this problem. There are 4 strategies, basically, that we've seen that work quite well. The first one is let's just extract every fact and preference. Right? And this is useful in applications like maybe a travel agent where you want to understand the user's preferences so you can recommend potential tours to them. And so behind the scenes, the agent memory server is actually watching your conversations with the user and persisting or extracting this information for you. You can also use summaries. If, for example, you don't remember everything a user has said and you want to just get a very finite set of that, you can focus on that. Preferences is also quite similar as well if a user prefers something to the other. And you can specify a custom strategy. So, for example, if you are building maybe a coding agent, you can say, I don't really care so much about summaries and I want to focus on like the technical architecture skills that a person has. So as the agent interacts with this user, it's automatically behind the scenes retrieves just memory related to that. And you can use different ones. These are just some examples. So if a user, for example, prefers Python over JavaScript, this is something we might want to extract. But also, please note the fact that we also extract the topics and the entities as well. Because if eventually you want to like find relationships with the entities, this becomes very useful. The summary, as I mentioned earlier as well, you don't want to go into the full project requirements. You want just the concise one. You can extract this behind the scenes, preferences, and then your custom strategy is what I mentioned earlier. So in this case, we want to focus just on architecture decisions, technology choices made, and implementation details. And the agent memory server behind the scenes can use an LLM to actually extract this for you. It's no longer the responsibility of the app layer to do this for you. And I mentioned about the memory management as well, and that not all memory is created equally, and we have to think about the life cycle. But one thing is some memory should have a time to live that is finite. And so Redis obviously has a time to live attribute, and you can set an age-based time to live to saying after 60 minutes I want this memory to be deleted, or I want this particular memory to be gone. You can also base the forgetting based on when last was accessed. So for example, if a user doesn't access this particular memory in a month, maybe let's forget that. That's something that's also possible, and also based on your budget. Right, but then there's also a recency scoring based on novelty and freshness. I mentioned earlier around accessing data on how recently it was used, and sometimes you might want a more soft type of decay. That the less something is used, the less it becomes more important to you, and the more something is used, the more that becomes important to you. Also, you might want to watch out for novelty, maybe from interacting with the user mentions a particular fact that just seems so novel to them. That might be something that you might want to use to decide whether or not to forget or not. So summarization, not to go into the details, but you can specify a summarization threshold here in agent memory server. And what this means is that the moment your conversations or context usage exceeds about 70% of the context window, it summarizes that for you and replaces the older messages with this new summary for you. 1 second. So I'll hand over to Raphael. We've got about 8 minutes to go through a quick demo.
Yeah, let's show you the demo now. The demo is probably the most fun part for me because I don't know if you guys think about it, but I'm trying to get out of this rat race. And that's why I'm building this stock analysis agent application. Let's see if this is still working. Let me zoom in a little bit. But I can ask questions such as, or say things like, hey, my name is Raphael. Takes a little while. It's a multi-agent application. I can say, what's the current price for Duolingo? Does anybody have Duolingo shares? No? Nobody? Only me? It was my best share and then my worst one after the CEO started saying a lot of things that he shouldn't be saying. All right. I can also say I own 20 shares of this stock. And pay attention that I'm not mentioning which stock, all right? So the agent memory server is smart enough to actually understand the entity that I'm talking about. And then I'm gonna say my wife's name's Marcella. Okay, he's probably gonna note it. And right now, I'm only storing working memory, all right? Behind the scenes, the server itself is going to extract the long-term memories. And then I'm gonna say she owns Microsoft stocks. And notice that I didn't mention who, I just mentioned she, all right?
Interesting to see what it does with spelling mistakes.
Yeah. And then I'm gonna say I prefer ETFs over dividend stocks. Now, I'm gonna go to Redis Insight, which is our graphical user interface for Redis. And apparently, it's not working as intended. Let's see if it extracts. No. Okay, I think...
Is it in the queue still being processed?
No, it's not the kill. I think I had some problems with Redis this morning with the agent memory server. So I have... Where is it? Okay, here we have it. Yeah, my memory worker stopped. And I think that's the perfect kill because we have two types of the agent memory server, the open source one and the managed one, right? That is being released this month. If I was using the managed one, then I wouldn't have had this problem. However, I am prepared. This is not going to be a troubleshooting demo because I also got a video of the demo itself. Nice backup plan, exactly. So let me increase the size of this. So you can see that I write, hey, my name is Raphael, I own this stock. And I continue, she owns NVIDIA stocks. She also owns Microsoft stocks. Okay, it's working just fine. And then I say I have 20 Duolingo shares. All right, then what I'm going to show you now, after I think I also talk about the ETFs and so on. And then I go to Redis Insight and I show the working memory first. So you can see here, I think I had already shown that. Okay. That's when I do it. Refresh it. And then you can see the extraction pending on the top. So this is the worker extracting the long-term memories. And then I open the working memory, as far as I remember, yeah. And I show you what the working memory looks like. And then you have the messages on the top there, which is a list of messages. And those are all the messages from the chat that is happening at the time, the session. So you can see a lot of messages there. You also saw that there is an user ID. And then you can see that it extracted long-term memories automatically for you, for me in this case. And so on. But then I'm going to show you in the actual agent what it's doing. So I can ask, for example, what's my current holding in Duolingo? What's the value of my current holding? And then this is a multi-agent application built with Spring AI. If you were at the workshop yesterday, you learned how to do the same thing. And then you remembered that I have 20 shares of Duolingo. It contacted a third-party API to get the current price and calculated the total price for me. And asked what stocks do my wife own, and he said that your wife owns NVIDIA and Microsoft stocks, even though this is a new session, all right? So the working memory is a new one, but it can still retrieve the right memories based on the context of the conversation. And it's doing so right here. And here I'm just showing the multi-agent part and the execution breakdown. So all the sub-agents that were triggered, but also the memories that were retrieved for this specific context right here. And that's basically the demo. I had to share. If I go back to the presentation, where was it? All right. There's also, I can also show you how you can integrate the agent memory server with Spring AI. So has anybody used Spring AI before? Okay, one hand. In Spring AI, they have the concept of advisors. And advisors are like interceptors. And that's what we use here for the integration. So what we want to do is we want to intercept the message that comes from the user, inject new information into this message. So you see that I have two different advisors here. Send that message to the model itself, OpenAI or Amazon Bedrock, you name it. And then you get that message back. You can also perform mutations on that message or other, you can apply new functions on top of these messages as well. So in our case here, we're going to have two different advisors, the chat memory repository and the long-term memory repository that we have to implement. This one is for working memory, and this one is for the long-term memory. Right? So once you get a request from the user, what Spring AI is going to do is it's going to inject all the session messages into the prompt, so the LLM has all of this information to complete your task. After that, we're going to retrieve the long-term memories from the agent memory server using the official SDK for that. And ignore these two messages here, allowed and no cache hit. This is from something else. This message is going to be sent to the chat model. It's going to do whatever it does and come up with a response. For the long-term memory advisory, we're not going to do anything after. But for the chat memory repository, then you're going to append the new message that came from the chat model in the session memory as well. So as I said, we have the official SDK that is going to give you the memory API abstraction to connect with the agent memory server. And this is an example of how you can implement your own chat memory repository for Spring AI. So this is an abstraction provided by Spring AI itself. And then we build a new one on top of that one. And the same thing for the long-term memory advisor. In this case, we're using the base advisor that is provided by Spring AI to build what's going to happen before and after the interception. So it was highlighting all of that. All right, and then all you have to do is wire that in your chat client as new advisors here in this case here. So you have the message chat memory advisor and the long-term memory advisor here for the chat client. And that's basically it. I'm just going to give you back so you can wrap up the presentation.
25 seconds, but just very quickly, what are the three main things we want you to remember? ULM memory is limited based on the architecture it was built on. Transformers are limited and stateless. Human memory offers us some insights. So for example, we can transfer memory from your short-term to your long-term by repetition. And the agent memory server is an open source library which allows you to implement this short-term, long-term memory in your agents without you having to do that heavy work of actually doing the implementation. We do have our LinkedIn names there, but also we have a copy of the slides and the GitHub repository to this particular demo. So please feel free to do this. I believe that is it. Thank you very much, everyone. We really appreciate your time.
Thank you.
Awesome.